this video, I'm going to describe the constructing evidence-based explanations practice in the context of the It's All Connected data puzzle. So the goal of this practice is to have students finalize new understandings about science ideas as they relate to the investigative question. And they're going to do this by constructing an explanatory model. So for this, we're going to have students construct these models, annotated sketches individually or in pairs. Before we have them construct their models, we want to first take some time to have students reflect on all that they've done up to this point. From the opening scenario to the interactive reading, the puzzle plot text, the data analysis component, a lot going on there. So we want to help students identify the important science ideas and any evidence they have to support those ideas that you absolutely gotta have in a final model for the investigative question. So we'll talk a little bit more about that in a moment here. And then we want to help students understand what goes into a scientific model, what that looks like, review different signs and symbols that help connect parts in a scientific model. So a few different scaffolding things that will help this practice be more successful for students. So again, students have just finished analyzing a data set and thinking about how evidence they gathered through that data analysis activity helped them understand the investigative question a little bit more clearly. And so now that we've gathered that evidence, it's time to construct the final model to explain the investigative question. What effect, if any, do leads, these large cracks in sea ice, have on the transfer of moisture between the Arctic Ocean and atmosphere? So what should be included in the final model? What does the model even look like? So before we start the construction, we need to figure out what a scientific model is, what it looks like. And to do that, I like to lean on something students are familiar with. And in this case, in the slide deck, that is a Marvel movie, a model about the movie Black Panther. Before we get into this model here on the right, what is a scientific model and how are they used? They're used by scientists to help them visualize explanations to questions they're investigating. So a perfect application for what we're trying to do here. And in a scientific model, what's included are relevant parts or concepts, signs and symbols that help connect these parts and concepts, and then any data or evidence that we might have. And so using this example here, this is a model that's used to explain why the Black Panther gets stronger after being punched. I like to have students see if they can identify these 3 bullet points by looking at this model. And so we've got lots of different parts, from a meteor impact that's depositing an element vibranium, which shows up in a key. You can see that vibranium is being mined here. This is a zoom in window to show what's happening on a scale we can't see. That vibranium is then being inserted into the suit. So different parts included, connection between parts with arrows and zoom in windows and keys. So lots of different components infused here. And we want students to, again, start to be thinking about how they might use parts of what they see in their own models. I think it's important to show this slide to students, maybe even print it out. It shows examples of different modeling conventions students could use to make connections between ideas. So arrows to show connection or the movement of things, keys to define symbols that are used throughout the model, text boxes, zoom in windows to show what's happening on really small scales, or timelines to show changes over time. Next, the gotta have checklist. So we know what a scientific model is and what it could and should look like, but we need to now think and reflect about the different ideas and concepts that should be included in a final model for this question. What effect, if any, do leads have on the transfer of moisture between the ocean and atmosphere? So in the student worksheet, students have a space to record different ideas that they think they just gotta have in a final model. They can record any evidence they have to support those ideas, thinking about evidence from the reading, evidence from the graph, and they create that list. An additional level of scaffolding is for students to take their own list and share those ideas with the whole class. And then as a class, when those ideas are shared, the class has to come to consensus and decide what goes on a whole class public record, a whole class gotta have checklist. These checklists are super important in helping students make sense of all the information that has been presented to them and provides a roadmap that they can use when constructing their final models. After that gotta have checklist construction, it's time for students to construct their final model for the investigative question. Here is the graphic upon which they are going to be annotating. So an image on the left that has no lead, no crack in the ice, an image on the right that does have a lead, a crack in the ice. And so they need to show what effect these leads might have on the transfer of moisture between the ocean and atmosphere. After students construct their model, we encourage classrooms to give an opportunity for students to share their models. Typically, this looks like a gallery walk where student models are left on desks or taped around the room, and students have an opportunity to kind of circulate. We've had some teachers use sticky notes, and as students circulate, maybe students write questions and leave them, or provide positive feedback, what they see, what they like on models as they move around. We'll leave that up to you, but really important that students get to learn with and from one another. The last piece of the constructing evidence-based explanations practice is to have students dig a little deeper and apply what they've learned to either a new scenario or kind of dig in a little bit more about the investigation presented in the data puzzle. And in this case, we ask students to think about how an increase in the Arctic's humidity, and as a result, an increase in the number of clouds, when you have increased moisture in the atmosphere, especially in the Arctic, that can trigger the formation of clouds. How might the formation of clouds affect Arctic temperatures? And so there's a little bit about that in the puzzle plot text, and we've got this graphic here. So what do students think? How might an increase in the Arctic's humidity affect Arctic temperatures? Encourage students to share their thinking with one another or as a whole class to this question before showing this video, Arctic Feedbacks, which talks about how clouds can contribute to both positive and negative feedback loops in the Arctic. And that concludes the It's All Connected data puzzle.